Hello friends, welcome to another tutorial in electromagnetics and antenna series. In this tutorial we'll talk about electric field intensity due to a line charge density. In the previous discussion we talked about various charge densities. We talked about line charge density, surface charge density and volume charge density, and we did a couple of numericals based upon those. Now in this tutorial we'll find out the vector E because of some line charge density on a line of wire. So if this is something that interests you, then please keep watching. The prerequisite to start this discussion is the understanding of Coulomb's law, and from the discussion of Coulomb's law we know that electric field intensity due to a capital charge Q on a test charge Q is given by E, which is of course 1 upon 4 pi epsilon naught Q upon R square, and it is radially oriented, and this is nothing but the force upon this test charge. This expression E is nothing but force upon the test charge. So that will be the starting point for this discussion. The objective here is to find the electric field intensity due to a line of charge with line charge density rho L. For that, for the sake of simplicity, I've taken up this coordinate system and I'll take up a point somewhere here on the xy plane, and on the z-axis I've taken up a line of infinite length which has a line charge density of rho L. So if I take up a point here, let us say this point is x, and you know that this point x has coordinates r, phi and 0 in cylindrical coordinate system. So the distance of this point from the origin is r, which is specified as radius, so it makes an angle of 5 from x-axis, and because it is placed on xy plane, so the height is 0, so z is 0. Next we consider a small differential length dz on this infinite wire with charge dq, and because of that small length dz, if I wish to see how much electric field intensity is being felt here at this point, that can easily be calculated. So that will be dE, because this is because of dq charge. In this small differential length the charge will be dq, and that will exert some electric field intensity at this point, which can be written as 1 upon 4 pi epsilon naught dq, which is the charge, upon r square, and radially. So the direction of the force will be here, the actual direction of the force will be here, right? So again in the next step I can convert this r square into r cube, making this as the r vector, and r vector is nothing but the starting point and the end point. Starting point is r minus 0 square plus 5 minus 5 square plus 0 minus z square, so it becomes r square plus z square. So coordinates of this point is 0, phi and z, by the way, because it is at a height, at some height, let us say z. So this is an important point. So this distance r from this differential length to this point is expressed as r square plus z square, and we substitute it here, and by the way, its direction will be towards this side, and which is r 0 and minus z. It is going towards minus z. However, this direction of this vector can be resolved into two parts. One is the normal component and one is the tangential component, so we can draw that as well. Now, why is that important to understand? Because if we would consider some differential length here, then the force would be exerted in this direction, and when the force is exerted in this direction, its component, it again has two components, and one component goes exactly in the opposite direction of this, which gets cancelled away. So the z components will get cancelled away and only the r components will get added up. So that point is super important. And taking this under root out, I get a power of 3 by 2. So while integrating over the entire length of z, we know that the z components are going to be cancelled with each other, because if we divide a vector into its two constituent components, and so all the components in the z direction, they will get cancelled with each other, and the r components are added. So what we are left with is the component in r direction only. So that is one important conclusion, that it is radial. The electric field vector, because of this line charge, is felt radially. And now comes the tricky part of expression generation. So E currently is extending from minus infinity to infinity, 1 upon 4 pi epsilon naught, and this dq can be written as rho L dz. Charge can be written in terms of charge density. We've discussed this so many times. So this is what is happening here now. And finally, we see that z, the height, can be written as r tan theta. The theta can be written as r secant square theta, the theta. Then limit changes from minus infinity becomes minus pi by 2 and infinity becomes pi by 2. So my E vector becomes minus pi by 2 to pi by 2, 1 upon 4 pi epsilon naught, rho L r square secant square theta, the theta, upon r cube secant cube theta. And of course the force is exerted radially. So you could pause this video down here at this point in time and note this very carefully, the transition going from dz to d theta. So this point is important. And taking rho L upon 4 pi epsilon naught r common, because we get a 1 r here left, we get cos theta d theta, and integration of cos theta will give me sine theta. The limits are minus pi by 2 to pi by 2, so which gives me 1 minus minus 1, so that gives me 2, and I'm left with rho L into 2 upon 4 pi epsilon naught r in the direction of radius. So this 2 is left here. So my electric field intensity due to a line with line charge density becomes rho L upon 2 pi epsilon naught r. So this is a very important result that simply shows that if you have a wire with certain amount of charge density and you wish to find the electric field at a distance r, it is simply rho L upon 2 pi epsilon naught r, and it is in the radial direction. So just moving outwards normally, all the components in the uh, z directions, they get cancelled away with each other. So that was it for today's discussion, and this discussion is super important because this will act as the fundamental concept if we wish to find the electric field intensity E vector for surface charge density also. So in the next video we'll find out E for the surface charge density. And if you liked the video, please give it a thumbs up, consider subscribing to the channel, share this video amongst your friends, and I'll see you around in the next video. Till then, take care, have a great day, good life, bye bye.